If the Mercator projection distorts sizes so dramatically, why does nearly every digital mapping platform continue using it? The answer lies in how online maps function at a technical level, not in geography or politics. Google Maps, Bing Maps, and most other web mapping services rely on Web Mercator, a modified version of the traditional projection that became the standard for digital mapping. Think of it like assembling a jigsaw puzzle where every piece fits perfectly. Web Mercator uses a grid of square tiles that cover the entire mapped world without gaps or overlaps. This uniform system allows computers to process maps efficiently as you zoom and pan. The projection's straight meridians and parallels intersecting at right angles enable seamless navigation. Alternative projections like Robinson curve their longitude lines, which would create irregular gaps between tiles or require complex stretching. Web Mercator avoids this by maintaining identical tile shapes at every zoom level. Only the geographic coverage changes. Mathematical simplicity gives Web Mercator another edge. As former Google Maps engineer Paul Rodemocher noted, the projection's constant angles let us calculate distances with basic trigonometry, critical when serving millions of requests. Other projections require spherical geometry that would slow response times. This efficiency becomes essential for real-time features like turn-by-turn navigation. The tile system also streamlines rendering. Map servers pre-generate tiles at various zoom levels using identical algorithms regardless of location. Whether displaying Paris or Tokyo at zoom level 10, the system applies the same processes, just with different geographic data. This consistency extends to overlaying information like traffic patterns or business locations, which align perfectly with the base map at any zoom level. Despite these technical benefits, the projection introduces significant geographic distortions. Alaska appears roughly 3 times larger relative to Texas than it actually is, while Greenland seems comparable to Africa despite being 14 times smaller. These exaggerations become glaring in global views where polar regions stretch endlessly. The tiling system also imposes physical limits. Web Mercator cannot show the poles, leaving Antarctica truncated or missing entirely from most online maps. Historical inertia cemented Web Mercator's dominance. Early digital platforms adopted it in the 2000s because it matched existing paper maps and GPS systems. Once developers built entire infrastructures around this projection, from coding libraries to server architectures, switching became prohibitively expensive. As cartographer John Hessler observed, the tech stack around Web Mercator is now so entrenched that changing it would be like replacing a city's plumbing while keeping the water running. Performance requirements further lock in the standard. Consumer mapping apps must load instantly on phones with limited processing power. Web Mercator's mathematical simplicity allows quick rendering without specialized hardware. More accurate projections often require additional computing resources that could slow performance or drain batteries faster, a trade-off most platforms won't make. Some services have implemented compromises. Google Earth uses a 3D globe that avoids projection issues entirely, but this demands significantly more processing power than flat maps. Mapbox and ArcGIS Online offer alternative projections as options, but default to Web Mercator for compatibility with existing systems. The commercial mapping industry recognizes these trade-offs. While paper atlases abandoned Mercator decades ago for balanced projections like Winkel-Tripel, digital platforms prioritize usability over geographic precision. Until another system matches Web Mercator's technical advantages without the distortions, it will remain the standard for online maps. These technical choices shape perception. Most people now encounter maps through interfaces that subtly reinforce Mercator's distortions through constant exposure. When you check directions on your phone, you're using a system optimized for pixels and processors, not one designed to represent Earth accurately. Alternatives exist that better preserve geographic relationships, each with unique strengths and weaknesses. The next section examines one such option, the Gall-Peters projection, and why its approach to map-making sparks debate among cartographers and educators.